All right, welcome to my talk using C++ as an optimizing assembler. So what we're going to do today is I'm going to show you how to write your own runtime. I have 3 goals for today. Is make this a fun talk. I'm going to try to get you to read assembly, and I'm going to give you something you can use next time you tackle a performance problem. So right now, what I want to do, the first goal is to write this hello world program using our own runtime. So I chose this specific version because it's really easy to implement, so it's good for a talk and a lecture. So if you've never seen write before, write is a PostX function call, and PostX says that standard in, out, and error have the file descriptor of 0, 1, and 2. So this slide says we're going to write standard out, hello CppNorth, 16 bytes. The 16 does not include null, but it does include the new line. So the first thing we want to do if we're writing our own runtime is not use the C++ runtime. So we do that by using dash no stdlib. Once you do that, the linker is going to complain because does anyone like linker errors? Neither do I. So it's going to complain about start missing and write. Write, we're going to implement using a system call. Start is the OS specific stuff that you have to do before you call main, because your main code might be platform independent, but the boot up code that's in start, that's going to be specific to each OS. So we're going to implement that. Before I get into that, I just want to go over the command line. So because we're going to be using this throughout the talk. -G, that gets us debug information. I assume all of you know it. -M means it's machine specific. So -M arc equals Haswell. That's saying we're using the Haswell architecture. So it's a 10-year-old CPU, but I'm specifically using this one because I'm using an intrinsic, and the compiler will complain about the intrinsics not existing unless you tell it what CPU you're targeting. So if you want to use newer intrinsics or you don't need it at all, you could just like replace this with whatever you want. So -no stdlib, as I said, it lets us not compile with the runtime, but it also prevents the standard library unless you want to implement all of the C++ standard library. So yeah, you don't necessarily need that. -static, that's not required. The program I end up writing did not load any dynamic objects. So since I didn't need to load any dynamic things, I put -static because that strips out the dynamic section in the executable. But you don't have to worry about that. That's not required. And I'm going to show you some assembly. So I'm going to give you plenty of time to read this. Take your time. You can read the comments. So you don't have to understand this. Just try your best. And yeah. Yeah. So I'm going to give you another 10 seconds. All right, so who knows why this is false? This guy assemblies. He's the only hand that went up. Correct, but so the problem is line 8. I'm doing a return, and you're returning into the void because there's nothing before starts. There's nothing to return to. So yes, you're supposed to exit, and exit as in the system call exit. So let's just implement that. And line 11 is the system call that exits. Now, this system call, it's a system call, but there's no labels, there's no addresses, it's just nothing, it's just system call. So it's a little different because you don't know where it's going to. The kernel specifies it, and you won't be able to see it. So the way the kernel knows what function you want to call is by putting an ID into a specific register. So that's line 9. So if you look at it, we're putting 60, which is the ID for exit, into racks. So if you remember in C, you can call exit and give it an exit code. So we're going to do that, and that's line 10. And that's going to look weird, so I'm going to explain it. So in assembly, you typically want to encode things as little with as few bytes as you can, so you can fit more instructions into a cache line. So if we did a move 0 into RDI, that's roughly 5 bytes, and this one is 2 bytes. But since I used 64 register, it's 3 bytes, but that doesn't matter. I just wanted it consistent. So that's why I use RDI. A lot of math ops, they use a source register and a destination register. So what you're seeing here in the XOR is DI equals DI XOR DI. So that's what you're seeing on line 10. So we compiled it, there's no seg fault, everyone's happy, and we have the exit code as 0. So why do we use RAX and DI? So the kernel has something called an application binary interface. So this is how the assembly and programs can ask the kernel to do things for it. So the API specifies that you don't have to take pictures. I'm going to link the slides at the end. But the API specifies how to communicate. And it says if the system, the function call you would like to call goes to the RAX register, and the return value is also there. And I'm probably going to say AX and DX and so on because the first letter is how many bits. So E is 32 bits, R is 64 bits. And it's not actually like 2 different variables. It's 1 variable with different amount of bits. So if you look at line 2 of this assembly, you see that I use DI. If you look at the parameter list, DI is first. So that's passing the first parameter into the system call that we want to make. And at the bottom is the prototype. So since our goal was to do a hello world, we're going to go over the write function. Line 3, load effective address, that's a little more complicated. So earlier I said that you want to have a shorter encoding if you can. So instead of having a 8-byte address, what the compiler is doing is it's doing a relative address compared to the instruction pointer. So a RIP, IP, that means instruction pointer. It's like where in code space are you? So that's a relative, so it's going to be much less than 8. It doesn't require 8 bytes, so yeah, it's better for the encoding. So since this function is three parameters, we need to use SI and DX, which is exactly why we're putting the pointer into SI and putting the length in DX. So now that we know how to do this in assembly, let's get back to C++ and implement this. So let's just first do something that's valid in C++. You don't need to implement a syscall. It's part of the standard. So if you compile this will work, but I wrote incorrect code because if you're writing your own runtime using the assembly at the bottom, it's not going to work because the args are not correct. But I just want to show you how to do how to implement the system call. We're going to do that for later. So in addition of the kernel having an API, C has an API. I'm not sure why the 4th parameter uses CX instead of 10, but it is what it is, and really it's not that big of a deal. You're not going to be writing the assembly. You're just going to be reading the assembly from optimizers and all that. So here you might see a lot of moves and think, is that going to be slow? No, absolutely not. Move can happen in the decode stage, so it's essentially free. It's in this when you're doing the actual instructions, it's probably not even going to touch this. It's going to be a no-op. The only part of this function that could be slow is line 13, which is the system call, and that's because the system call you're making might not be in L1 cache. So at minimum, you're going to be waiting for the L2 cache or even main memory, which is even slower. It's probably not going to be in main memory, but yeah, that's the only thing that's slow, and there's nothing to optimize in this function. So yeah. So our original goal is to write hello world like this, like how you would do it in a standard program. So it took a bit of finding. It's really hard to Google search this, but I figured out how to get the argc and argv, and instead of calling main, I'm going to call our own int function. So line 2 and 6 is not important. I put 6 in because line 2 causes a warning if you don't have line 6. So yeah, it's pretty simple. I just call main, get the exit code it returned, call exit with it, and no, pretty straightforward. The write is just making that system call that we just implemented. So it's pretty straightforward. But this is incorrect because postx wants -1 if there's an error, and system call is not going to return -1. It's going to return whatever the OS returns. So we're going to have to change that. Because I wanted to use this with a multi-threaded program, I implemented error no using thread local, as you can see in line 2. The macro uses a function called error no location, so that's line 3. Pretty simple. And line 7 checks if the result is in a valid range. So if it's 0 or higher, it's valid. If it's less than 4095, then it's also in valid range. So I guess the -4K space is reserved for error numbers. So now that we returned -1, we're all good. Or so I thought. So I was getting frustrated at this point because I knew the problem had to do with thread local, but I had no idea how to fix it. So before I go into the assembly, I'm just going to go over the first line. It's very handy to dump the disassembly into the terminal, so that's what I'm doing. And if you look at the top right, I do set disassembly flavor Intel. Everyone says that Intel is more readable, and I agree with them. So the rest of the assembly is going to be in Intel, and I hope you're glad. I see some thumbs up. Great. The easiest way to know if it's Intel or AT&T is AT&T has the percentage in front of the registers and a $sign before the variable in front of the literals. Intel does not have either. So yeah, and they swapped the source and destination in the instructions. So if you look at line 13, that was the line that segfaulted. So what we're doing here is we're moving the AX register into FS:4. Now, I had no idea what that meant. So FS is a general purpose segment register, and the value was 0. So this was trying to move into -4, not valid memory space, and why we got the segfault. Keep in mind that the value is -4, because that's going to be on the next slide. I looked up how to calculate the FS. So essentially, the FS is an 8-byte pointer. So it dereferences the pointer. Whatever value's at that, it's going to, like, it's loading, so that's why I said dereference. It's going to subtract 4 from it. And then the move on this line dereferences it again. So that's 2 dereferencing happening on this line. So now let's fix this. We only need 1 int worth of memory for the thread local, but x86 and Linux uses 4K pages, so I'm allocating 4K. If you search up if you look at the man page for mmap, it'll tell you what the parameters are, but it's essentially doing a kernel call to get some valid memory that we can start using. So TLS memory is a pointer. So line 9 is a little funny because I would just always assign it immediately. But if I did that, I would have to implement more of the runtime, and it's not good for a talk. So we're going to skip that so you guys can try this at home without like trying to implement more. So line 10, we're adding the size to memory because we want the top of the memory address. So stacks, I don't know if you all know this, but stacks, they start from the top and they go downwards. And in the last slide, I said, remember that we're using -4? It's using it as a stack. It's going backwards or downwards. So that's why we're setting the value to the top. So I mentioned that there's two dereferences, and the fs gets dereference, and then it adds the memory location. So that's why I'm doing getting the address of that variable. So, and that variable is static, so it's in global space, and yeah, so all good. I see a few nodding heads. All right. So no more segmentation faults. I was very relieved. So we also see, yeah, nothing else broke. We print the exit code, it's still 0. Everything's good. So let's clean up this code and make it work for another example. So this is also really simple. We're going to open a file, write to it, close. So this is actually almost the same as the write function we implemented earlier. If you look at line 11, you can see I'm declaring 4 different functions: open, read, write, and close. We're not using read, but they go together. So so I'm passing the name into the s macro. That's on line 3, and so earlier I talked about the C API. We know that the first 6 parameters are passed as registers, so we don't have to touch the stack. And that's why it's okay that we're using 6 parameters here, because open, read, write, and close definitely does not take 6 parameters. But that's fine. And the system call is not going to use those parameters if it doesn't need to. So this code will work perfectly fine. And yeah, it does -1, just like PostX functions like wanted to return. So we compile that, we run it, it works perfectly. Now we could actually start implementing real programs and using our runtime and thread locals and all that. So optimization. The first rule of optimization is you measure. You always measure. I hope you guys know that, and if you didn't, please remember. So what I like to use to measure is perf on Linux. So you don't have to do any source change. You just compile it with an optimized build, unless you want to measure debug build, which you probably don't. -G for the debug information. So when you do your reports, you can actually see the function names instead of the addresses. And once in a while, I'll use perf stats, but that's like a general statistics. Like it'll tell you how many, the percentage of stalled instructions, cache misses, and a few other information. I don't use that too much. You don't have to worry about that. But it is it's an interesting look if you feel like looking. Perf list has a huge amount of events. So a lot of events are kernel and hardware, and the hardware ones depend on your specific family of CPU. So it might change every process or every CPU you buy or test with. The one I use the most is cache misses and stalled cycles. They both give similar results, so I just wrote cache misses. So what I typically do is I do a perf record, decide what function I want to optimize, look at it with the cache misses events to make sure there's like not any easy things I can do with just by fixing up the memory or avoiding loading extra memory. And then I go back to perf record, which does cycles. I believe it's both stalled and non-stalled cycles. It's like the total time. So you just rinse and repeat a few times, and you should be able to figure out like most of your slow functions. Now, I2A means integer to ASCII, like printable text that you would have in a text file. So I noticed I was in my real app. I noticed I was taking 1.2 of the time, and 1.2 of a 1-second app is only 12 milliseconds. And do I want to optimize 12 milliseconds? I don't, but does make a good example. Yeah, so we're gonna optimize I2A. So if you go into perf reports, you'll see something like this. The left side is the percentage of time that instruction took relative to the function. So typically you'll see the numbers clumped up, but it's not clumped up in this situation. The reason why it's clumped up is because the beginning and end of a loop, it's either mispredicts or where you're loading and storing to memory. So that's where it's usually long, but this is pretty steady. So I'm guessing, well, I already know it's not using a memory operation, but yeah. This is also a sign of lack of instruction level parallelism. So on a CPU, there's something called a port. Ports do different things, but since add, subtract, shift, and all that, they're so simple. A few ports, more than one ports will implement it, and some of the things will overlap. So you can have 2 adds, 2 subtracts, or an add and a subtract happen on different ports at the same cycle, as long as they're not depending on each other. So if I say there's a lack of instruction level parallelism, it means all the instructions have to be ran through sequentially, and there's no, it's not using up all the ports, it's just using one at a time. Before I go through this, I just want to point at line 3. So over here, we're doing multiply R10 with EAX, or the AX register. So most instructions is affecting 0 or 1 register. I multiply will affect 2. So it's AX and DX. However, if you look at the very next line, line 4, we're overwriting AX. So because we're overwriting it, they can be done in the same cycle. So I just wanted to point that out. So take a look at line 12. So CL means the low 8 bits of the CX register. I'm going to go from the bottom all the way to the top. So we're moving the CX register into memory. Where's CX being stored? The line right before it. So CX, that's both the source and destination register. So where's that being modified? No, the line before. That depends on DI, the line before. That depends on DI again, the line before. DX, the line before. Again, the line before. And at this point, it's not the line before, but that's because it's the multiply, which at minimum takes 3 cycles on most CPUs. So this entire loop is entirely sequential. So instead of trying to optimize this at assembly level, we could just change algorithms. Maybe we can do 2 digits of I2A instead of 1, and maybe we can use some instruction level parallelism by doing that. So when I wanted to do some micro benchmarking, I like to use NanoBench. There's more than one program called NanoBench, so here's a link to it. You can get the link at the end when I link to the slides. So if you look at my main function, it's very simple. I implemented a few functions, and I call test. Test is a macro, even though I have a lowercase. And I just want to bring your attention to line 4. So this is not guaranteed to work. Essentially, I don't want the functions to be optimized out. So I'm going to attempt to trick the optimizer into thinking it's not a literal. So that's why this function exists. And yeah, it's pretty simple. But if this currently works, but if it doesn't, I have to do something more extravagant. So hopefully it works for a long time. So if you look at line 14, those are all my test values. The first half of that large macro at the top is doing a unit test. So I want to know that when I implement the function, if I did it right, because it's easy to get fast results if it's not correct at all. So line 9, as you can see, I'm using the non-literal hack so the optimizer doesn't optimize out the function completely. And line 10, 11, 12 is NanoBench. NanoBench GitHub page is, it has like a hello world program. It's extremely simple. I don't have to walk through it. Run CC it, you'll understand how to use it. Typically, I would use templates, but for whatever reason, the templates was using an indirect call to my function. That was affecting the timing, so I had to switch to the macros. So it gets a little finicky when you use NanoBench and you do this kind of thing. So here's I2A. If you look at the very bottom, 13 and 14, you can see that I'm dividing by 100 instead of 10. That's because I'm going to be doing 2 digits at once. This is in the I2A that I started with. Line 4 is actually very handy because a lot of my values were 1 and 0. So that actually made a noticeable difference. The if statement on line 5 is horrific. I don't know how I implemented like that, but I guess I was just copy and pasting thing, and it just sort of happened to look like that. So I did this like much nicer, and I noticed the timing change. That was very surprising to me. I had no idea why. And this is the sort of thing that, this is like a trimmed down version of what Nano Bench would show you. If you look at line 1 and 4, you can see it's like a full decimal larger than 5 and 8. So I knew something was going on. So now that I showed you a lot of assembly, hopefully you can read assembly. So at the very top, you can see that I'm not doing set this assembly flavor. And that's because I moved it into a file called .gdbint. So that will execute every time you call gdb. And since I always use Intel syntax, I just put it there, made my command line shorter, which is nice. So that's why you don't see it here. So I dumped the code into my terminal and I read it over. And the very first line basically told me what was going on. So the other versions of I2A was not pushing, was not trying to preserve a register. This one is. So it's preserving the BX register. Not shown on the slide, and not that I noticed right away, is the negative case was doing a recursive call. So I guess that's why I want to preserve the register. And so I looked at version 2 and saw it was not doing that, and it was not doing a recursive call. So why is that? So I kind of had a feeling that maybe it thought I had to do the negative sign after the function call. So I just moved it up, and it turns out that was it. And I suspect that most of the time, if you're touching memory after a function call, it expects it has to be there, and it doesn't try to figure out if it should be if it can be moved up. And maybe the optimization win is typically non-existent. So I guess it just doesn't bother to try to find it. So if you have functions you want to be fast, you definitely want to measure it, or at least look at it through perf, because you'll see things like this. So yes, I just want to show you the rest of the function. I use a lookup table to do 2 digits at once. I thought it was fast. Nano Bench said it was fast. I put it into my program, and as you guess, it was not fast. So somehow it got slower, even though I measured. So it turned out that my original count digits function was using a lookup table, and I didn't realize that when I was calling I2A, it was in the time that my program was memory saturated. So using a lookup table was not a good idea. And I guess it was hitting the L2 instead of the L1. So I implemented count digits like this. Now, I'll just go through it quickly. It tries to figure out how many digits the integer is by looking at 16, then 8, then 4, 2, and 1. It's doing this as little if statements as possible. There's 5 if statements, and if branch mispredict is about 2 cycles, at least on my CPU. So if there's 5 if statements and 2 nanosecond mispredict time, that's about 10 nanoseconds. L2 is about 10 nanoseconds. So you're essentially gonna always do better with the branching if the data might not be in L1 cache. So I put that into my program. It was faster. So yeah, I think, does anyone have any questions on what we discovered? Yes.
I'm just wondering, could we have forced the lookup table, since it's so small, to be in the instruction code instead of in the data?
I was wondering about that too. So the problem is, it's not about the cache line. It's there's two parts of L1. There's the instruction cache and the data cache. The code is in the instruction cache, and you can't access the bytes like that. So it has to be in the data cache. So even if you fit it in the same block of memory, it's going to be in both instruction and data. So that's not going to work. But that was a very interesting thought, and I thought of it too. So that's a great question. Anything else? All right. Yeah, no hands. All right, I just want to touch on this really quickly. So I'm saying this in a specific way. A guy on the internet told me std vector does not use realloc. So obviously, I would not trust some stranger. I don't know his skill level. I don't know what he knows. And I didn't know anyone that's part of the committee or read the standards. So it's not like I had anyone to ask. I tried searching on Google, and at the time, I got no results of if it used realloc or not. So there's two valid answers to this, or two valid steps to take next. Either read the standard, which I did once and don't recommend, or do an experiment. And experiments are great because it helps you build your mental model of things. So if you look at the first if statements, that's the C++ way, and I find that much more clear than the other one. And all we're going to do in this code is push 20 million elements into an array. And then the writes is basically so it doesn't optimize out. And yeah, I'm just going to time this. That's all I'm going to do. The elements are 8 bytes. It looks like there should be, it should say long in the vector tag. I guess I didn't notice that until now. But yeah, I'm pushing 8 bytes at a time. So it's going to be roughly 160 megabytes. And even though the C code is going to be inline because like pushback doesn't have to be inline, but even though it's not, pushback is not inlined, all the memory is, all the time is going to be from fleshing the L3 cache into main memory. So that's where all the time should take. So I ran this, I timed it, and yeah, it turns out the guy was right. So sometimes people on the internet can be right. It's about 33 milliseconds slower. I don't think anyone cares it's going to be 33 milliseconds slower. If you're doing game programming, that's 2 frames, so you would care. But for the rest of us, you know, it doesn't matter. But now we know that vector does not do realloc, and you know it's helping us build our mental model. So is learning how to use perf or read assembly and understanding what your code doing at a low level worth it? So I applied all my knowledge to a program I was writing. The program is a compiler. It's a high level, it uses high level syntax. The goal is to be memory safe, produce code as efficient as C++, and not use GC or reference counting because I wanted to be as fast as C++. But since it's safe, you're not going to be doing tricks, and I don't think I can implement the compiler in this language. But the idea was I can use this on servers and microservices. So yeah, it's not going to be replacing C++ anytime soon. I don't want it to. So the question is, did everything I talk about help me write a fast compiler? So not only does it have to be fast, but does the code actually perform as well as C-generated code? So it does, but that's out of scope. So you could just confirm later if it does or does not. But right now, what's in scope is, does it actually perform well? So what I did was I wrote a script that did a lot of array assigns. The reason why I did this specific thing is because in most languages, you don't have to go through the standard library to assign to an array. It's built in. If I want to test this on other languages, I know that since I'm not doing an add or multiply or any of that, it's not going to do an overflow check. And since we're not using sanitizers for this test, this is going to be timing debug builds. Since we're not using sanitizers, it's not going to be a rate check. So it should be a fair test. Maybe someone from the committee can tell me if I'm wrong, but I don't think anyone's from the committee here, but so that's why I chose this specific test. Also in the language, it's called Bolin. Bolin. It enforces you to prove to the compiler that it's not going to be out of bounds, and I want to show that it's not going to be slow. So that's why I did this test as well. So I hear people say that Go is a fast language or a fast compiler. So I tested with that as well. And here's the Bolin version. You know, they're all pretty similar. So results. I'm going to explain the results before I show you the Bolin's results. But yeah, I just wanted to say that the result of Go surprised me because it ended up being the slowest, like slower than GCC and Clang. And the thing is, Go uses multiple threads. And I compared it to a single-threaded Clang and GCC, and they both outperformed Go. So at least for this test, Go was not fast. So, but since we all do parallel builds, I want to measure that, and that's about 550,000 lines per second. Now, realistically, we're probably going to be using sanitizers, but this is just to get an idea of like how fast a debug build would be. And I'm saying debug specifically because it's going to emit all the code. You're going to be able to step through all the code, and most of the time we're doing a debug build. So now that I went through all this, do you guys think I can reach Clang and GCC's speed, even though they have millions of dollars poured into it? Do you guys think I can get 1 million? Okay, I didn't get close to 1 million. I got 3 million. I didn't know compilers could get that fast. So 3.1 exactly, but yeah. That's the end of the talk. You guys can email me questions, or I'll try to answer some on the Discord if you think of it later. And yeah, I can take questions now.